So for section 4.8, we're going to talk about two theorems. The main theorem is what we call the mean value theorem. Rolle's theorem is a part of the mean value theorem. So it is allowed to abbreviate their mean value theorem as the MVT. So let's talk about what the mean value theorem is and then some examples of it. So the theorem of the mean value theorem. So we have a continuous function on a closed interval from a to b, and it's differentiable in the open interval from a to b. Then what the mean value theorem states is there is at least a point C in a b such that at f prime of c, f of b minus f of a all over b minus a. So what this means is you're looking at the value of the derivative at a particular point on the curve. So we're looking at the slope of your tangent line, and what this theorem is stating is that there's got to be at least one point where the slope of your secant line is equal to the slope of your tangent line. So here's several examples visually on a graph. So notice you have a point on AB, and I can draw my secant line. Remember, a secant line intersects the curve at 2 points. And at this particular C value, then the slope of my tangent line will be the same as the slope of this particular secant line. Here's another example. Again, we've got my secant line from A to B. And notice at two different points, we can find that there's two different x values at C1 and C2, where the slope of your tangent lines is the same as the slope of the secant line. So verify the hypothesis of the mean value theorem is satisfied on this interval and find all values of C in that interval that satisfy the conclusion of the theorem. So first of all, anytime when we're talking about C, we're talking about a particular x value. So first of all, we talk about the hypothesis. You have to state the hypothesis of the mean value theorem. First of all, the first condition is that f of x is continuous in the closed interval 1 to 4. And you have to state the second condition that f of x is differentiable in your interval 1 to 4. So again, they're giving you the interval. So you have to state the conditions that f of x is continuous in that interval and it is differentiable. So the conclusion. So first of all, f of x is 5 minus 4 over x. So your first step is you're going to find the derivative of f of x, which again we know is slope. So the derivative of 5 is 0. So again, we can differentiate negative 4 over x. We could rewrite f of x is negative 4x to the negative first. So when I use my power rule, that's going to give me 4x to the negative second, or 4 over x squared. Now remember, we're trying to solve for a particular c. We're trying to solve for a particular x value. So then f prime of c is equal to 4 over c squared. So now what we want to do is we want to find the slope. So we want to find our f prime of c to be equal to f of 4 minus f of 1 all over 4 minus 1. What that's giving us is it's giving us the slope of our secant line. So f of 4, again, when I plug 4 back into my function, I know 4 over 4 is 1. So 5 minus 1 is a 4. Minus, plugging in a 1. So 4 over 1 is 4. 5 minus 4 is 1. Over 4 minus 1, which gives me 3. So what I know is that f prime of c is going to be equal to 3. Over 3, which is equal to 1. So that f prime of c is equal to 1. So this is where I'm trying to find where is the slope of my secant line equal to the slope of my tangent line, which all has a slope of 1. So remember what I found f prime of c to be equal to. F prime of c is equal to 4 over c squared. So what I'm going to do then is I'm going to take my value of my slope of 1, I'm going to set it equal to 4 over c squared. Cross multiply, c squared is equal to 4, so c is equal to plus or minus 2. However, remember we're only looking in the interval 1 to 4, so I can disregard negative 2, so I only have at one particular c value. So at x equals 2, I know in this particular interval the slope of my tangent line at x equals 2 will be equal to the slope of my secant line.